Everyone, welcome back. In this lecture, we're going to be discussing about assertions and a basic overview for system Verilog assertions, how we can write assertions for in system Verilog. Assertion is simply a check. The idea is to validate the intention of the designer. So, as we always do, we verify the design. Assertion simply validates your design that the design meets its specification. Okay. You can write test bench assertions, interface level assertions, chip level duty assertions, and block level assertions, and you can also specify different clock domain assertions. Also, you can write assertions for formal checks, formal verification tools, also the timing level assertions that you want to check min pulse width or max pulse width, those kind of assertions. Let's say for an example, how you can specify the behavior of these two signals, okay, in system Verilog. So what it is here that the signal A, okay, it toggles to high, and the signal B follows signal A, or in other words, B will be toggled to low after 1 or 2 clock cycles. A is triggered to high. Okay, so we want to verify, or we want to validate this behavior or this situation, and it is supposed to be true all the time. Okay, so very simple check how we can write a 2-line code in system Verilog. Simply we can specify a property check P at the rate at passage clock. Okay, so positive edge or rising edge of the clock, if signal A rose, okay, goes to high, and that follows after 1 or 2 clock cycles. Double hash is nothing but the delay. 1 to 2 means 1 to 2 clock cycles. Signal B falls. Signal A, say for example here, this is the clock edge, signal A rises. So after 1 clock cycle or 2 clock cycle, signal B falls. And then after specifying this property, you just simply assert, use the assert statement and assert this property. Assert property check P. So what this statement will do, that it will continuously check that whether the signals are validating this behavior or not. If not, then simply you display the error. Now, it also may happen that your stimulus may not trigger that particular behavior, okay? But you want to cover that, okay, I have my test cases have covered all the properties, or if is there any property is being untested by your test cases, you want to check that. So basically you can write a cover statement in your coverage module that it will cover this property check P. Okay, and if this property is passed, then it will simply say check pass, means this property is being exercised by your stimulus. Okay, because what happens that your stimulus may not trigger these two signals A and B. Okay, so if the A and B are not triggered, then assert statement, assert property, it will basically be useless, for example, because both signals are not triggering, right? But you can catch that in the coverage report if you specify the cover property, that statement. Okay, very simple. Now let's talk about broadly system Verilog assertions can be classified in immediate and concurrent assertions. Immediate assertions are simply that they test for a condition at a current time, and concurrent means that they test for a sequence of events spread over multiple clock periods. Okay. For an example, immediate assertions, you can simply write it. For example, you want to check that your state, okay, state of a state machine is one hot encoded or not. Okay, if it is not one hot encoded, then you display a fatal error. So that's a simple check, and it will be checked at the current time. Okay, always whenever the state is triggering. Okay. Now for the concurrent statements, it's like the events are spread over multiple clock cycles. For example, in this example, the request, okay, request signal goes to high at the first clock. So 0, 1, 2, 3, 4, 5, 6. These are basically representative of the clock edges. Okay, and the acknowledgement goes high after 2 or 3 clock cycles. Okay, how we can write assertions for this behavior? It is very simple, as we discussed on the previous page. Very simple, that we can specify a property and then assert the property. So either way, you can specify property separately and then assert the property with the property name, or in one statement you can write assert property at passage clock request calls high, and then hash hash is the delay 1 to 3 clock cycles. So after 1, okay, 1 or 3, so it may be 1, 2 or 3, right? After these many clock period delays, acknowledgement goes high. Okay, or acknowledgement follows the request. Okay, if this property doesn't hold, then error message will be displayed. So how simple is that? And you can basically combine immediate or concurrent assertions and can write complex system Verilog assertions for validating your design intent. All right, let's take a look at a few more complex examples. If we talk about multiple clocks, all right, so a very simple example here. This is a pulse, okay, this input, okay, this is giving you a pulse, and it is being synchronized and going to a different clock domain. So basically what it is that if there is a pulse at the input, it will follow at the output. So here we are basically putting a NOT gate, and this is generating a pulse in clock domain 1, and we should verify or validate this in the second clock domain at the output port. Okay, so how we can write this design intent? Very simple. We specify a property pulse check at passage clock 1 in, means in, and then we specify the second in the second clock domain passage clock 2. After 2 to 3 clock cycle, you get the output. Okay, so this simple 2-line of code will validate, okay, whether the pulse input is at the pulse output. Okay, now let's take another example of multiple clocks where the multiple clocks are used in a typical asynchronous FIFO. Okay, so this is a typical block diagram of asynchronous FIFO, where you have write control logic, read control logic, okay, and you're accessing data in a RAM. All right. So how you can write the data integrity behavior for this scenario or for this block? Data integrity simply means that you are reading and writing the data in the right order, okay, and right number of bytes, simply. So let's say we specify a property, data integrity, and at passage write clock domain, write count how many bytes we have written, and we validate the data. Okay, data is equal to w data follows we want to read it in a read clock domain at passage read clock first match some delay 0 to a number of cycle when we get the first match, and then we compare, okay, the read, okay, this read is high, it acts as a read enable, and R count means number of bytes you have counted, what you have read, okay, and which is equal to the R data equal to data. Now here you see data is a internal variable where data holds the same data what we have written, and we are comparing the data against what we have read. So this is a simple, property statement, and you can assert this property. All right. So if you don't use the assert statements, the properties, as you have written a piece of logic, but it will not be exercised until or unless you use the assert statement. All right. So the assert and this property. Very simple. Well, some tips. Okay. Do not duplicate the RTL. Typically what happens that when the RTL designers, they want to write assertions, they are already thinking in the terms of logic. So do not duplicate. That's a first thing, that be careful that you are not mistakenly duplicating the RTL when you are writing the assertions. Okay, so it's always better to write assertions by somebody else other than the block designer. That's a good practice. But if you are the only one in your team who is responsible for writing the RTL logic and assertions, be careful that don't duplicate RTL. And the idea here is to capture the intent, not the logic. So you need to capture the intent, what is the intention of this piece of logic or RTL logic. Okay. It's a good idea to add assertions through RTL design process very early in the design cycle. That will save a lot of time, and also it will save you for the effort spent in finding the bugs and correcting them later on in the design process. It will save a lot of time, a lot of effort if assertions planning is done in the beginning of the RTL design process. Also, you may think of if some assertions did not catch a failure, means that you need to write more assertion, or you need to modify that assertion to catch that failure. Okay, and always think in terms of reusing the code. So like we do RTL code reuse, same way we need to think in terms of reusing the assertions written earlier for another block. Reuse, important. And a big question, often we struggle, who will write the assertions, design engineers or verification engineers? Well, the short answer is that both. You are developing a test bench, okay? What if the test bench is wrong, itself is wrong? How are you going to check it? Okay, so one level of assertions, you yourself make sure, validate that your test bench is right. Also, at the chip level assertions, it's better the verification engineers write those assertions whose responsibility is to just see at the block level, at the black box, like a black box. They know the input and output and the appropriate behavior. So that's the verification engineers. They should write at the chip level or top level assertions. And the design engineers who are writing RTL code, they should, if they write at the block level, basically it makes everybody's life easier. So at the in short, at microarchitecture level, okay, or block level, it is the design engineer, and at the chip level, it is the verification engineer who is going to write the assertions. All right. Now, some few keywords associated with the assertions: assert, property, cover. We already discussed these three. Assume, that we want to assume certain properties throughout our simulation cycle. Expect, we want to expect that behavior written in that property. Sequence of events, and so on. Main or assert, you want to assert. Assert came from the assertions. You want to assert certain property or certain situation to be true all the time, or you are basically validating it and property. Okay. Cover is for coverage. Thank you very much, guys, for listening this short lecture on system Verlog assertions. If you are struggling with any of the subject, you may contact for private lessons. Nevertheless, I thank you once again for subscribing and liking LeProFesseur on YouTube, and for your wonderful comments. Do not hesitate to write me back if you need more lectures on any other subject or any other topic. I would try my best to do some lectures on those topics. All right, have a wonderful day.